Hi, my name is Andrew Knight. This will be just a very brief video explaining why the classic Schrodinger's cat thought experiment is actually impossible, even in principle. So essentially, what is it? And it's basically the same, by the way, as Wigner's friend, which is the conscious counterpart to Schrodinger's cat. So essentially, we're talking about a quantum superposition that is macroscopic. And what I mean by macroscopic is that it certainly includes anything visible, such as a human or a cat. We're not talking about buckyball molecules or anything like that. We're really talking about something that is, at the very least, visible. And ultimately, that macroscopic quantum superposition can actually be measured by some interference experiment that is, in principle, possible. And I'm going to try to show right now that that is actually not possible. So classically, what we do is we look at what's called a von Neumann measurement chain to create a superposition by amplification. So essentially, let's look at some container C inside which we will have the Schrodinger's cat, or in this case, the Wigner's friend thought experiment at some time t0. So initially, there's going to be some tiny object O in some superposition over distinct states A and B. That is, they are separated by some distance that is significant relative to the size of the object itself, so that they are semi-classically located at either location A or B. Next, we have some sort of a measuring device that's in some initial measuring state, M0. Inside, we have Wigner's friend, F, who is also in some initial state, watching that measurement device. And then outside, we have Wigner himself as sort of an external super observer. Now, as it turns out, it doesn't really matter whether or not Wigner is isolated from this container, although in all the literature they always say that he is and must be isolated. But for the moment, I'll just assume, okay, such isolation actually is possible. So traditionally, what we say about this evolution is the following. Initially, the state looks like this. So this is the initial state of the object, and these are the states of the measuring device, the friend, and Wigner. After time 1, what happens is there's a correlation event between the object and the measuring device, so that now the measuring device evolves into some sort of macroscopic state A or B. We call those pointer states. So in other words, there may be some sort of indicator or pointer on the measuring device, so that if it measures the object in A, then it points to A. If it measures it at location B, it points to B, something like that. And then after that, at some time 2, Wigner's friend observes the measuring device and then also gets correlated, so that this state right here corresponds to Wigner's friend in a state of having observed the measuring device, an indicator state A that correlates to the location of object O in position A. So notice at this particular moment, what is usually said is that, well, Wigner himself is not adequately correlated to the system inside the container. Therefore, in principle, Wigner should be able to do an interference experiment on this system to show that this system is in a superposition state. And then after, if Wigner does not do that, or at some point Wigner opens up the box and finds a dead or alive cat, or in this case a friend who has observed either state A or state B, at that time t3, then Wigner himself becomes correlated to the system, so that this corresponds to a Wigner who happens to have observed a friend who said, hey, the measuring device said A, and that corresponds to, etc. Now, one thing I want to point out here is that we are assuming a no-collapse hypothesis about the wave state. We assume here the universality of quantum mechanics, at least to the extent that it is possible to create Schrodinger's cat or Wigner's friend. So, in any event, no matter who Wigner happens to be, whether it's Wigner A or Wigner B, the point is that both of them are correlated to ultimately a location of the original object at A or B. So that's the idea, is that there is some non-zero time between time 2 and time 3 in which some observer, Wigner, can do some interference experiment to show that the system inside the container was in fact in a superposition state. That is Wigner's friend, or Schrodinger's cat. Here's the problem with that. If instead of looking at the system from the perspective of an external observer, we actually look at it from the perspective of the object itself. So if you were an observer sitting on that object, whatever that would feel like, instead of, you wouldn't of course see yourself in a superposition, rather that object would see everything else in a superposition, everything else around it. So it would see the container in a superposition of locations, say CA and CB. The measuring device would be in some superposition of locations, so would the friend, and so would Wigner. Now, if in fact this perspective is physically identical to the previous perspective, and it is, although the relativity of superpositions is a relatively new concept in the literature, if they're the same, then the perspective from the point of view of the object should be correct and might lead to new insights. So in this case, at time 0, the object is still not correlated to the system, but notice that the system from the object's perspective looks like this, and notice here that Wigner in the position WA is already correlated to the position of the friend in position FA, who's correlated to the measuring device in position MA already. So now at T1, of course, there is that correlation between the object and the measuring device. But all that happens there now is we then get a correlation of the object located at some position A correlated with the measuring device located in position A and having measured the object in position A relative to it. And notice that at time T1, the friend hasn't yet observed anything. So the friend has not yet evolved into a macroscopic indicator state of having observed the measuring device, nor has Wigner evolved into a macroscopic indicator state of having talked to the friend who has observed the measuring device, and so forth. But the point is, notice that we still have completely entangled states now between the object located at A and the measuring device having measured it at A, and so forth. And so at time 1, we already see this complete entanglement of Wigner with the friend, with the measuring device, with the object. Now, it's at time 2, oh yeah, so here, note by that time it's already correlated, and so that means that Wigner, even at time 1, cannot do an interference experiment to show the object in superposition, because no matter which Wigner happens to do the experiment, that Wigner is correlated to a particular state of the object, so cannot show a superposition of that object. Now, of course, as the system evolves at time 2, all that happens is now the friend now evolves into an indicator state, some macroscopic state in which he has observed the measuring device reading A etc., or in this case, measuring B. And then at time 3, now Wigner has opened up the container and is now correlated to the friend and therefore correlated to the object. But what's important to notice, and what this sheds light on, is the fact that the correlation between the object and Wigner already completely existed at time t1 simultaneously with the correlation event between the object and the measuring device. So if that's true, there actually is not just a short time that you can try to expand by isolation, but rather, in principle, 0 time in which Wigner exists, or rather, in which Wigner can do an interference experiment on the system contained inside container C to show that it's in a superposition state. Therefore, what this implies is that macroscopic quantum superpositions cannot be demonstrated by any interference experiment, even in principle. It's just not possible. Schrodinger's cat, Wigner's friend are not possible in principle. It also implies that quantum mechanics is not verifiably universal. The idea is that maybe the wave state as it entangles with the rest of the world continues to be linear, but that may not be true. But the point is, this analysis shows that it cannot be verified because there's no experiment that can be done to show any macroscopic system in a quantum superposition. It also shows that the consciousness causes collapse hypothesis is false. It's the hypothesis that consciousness itself induces collapse of a wave state. Now, I haven't assumed collapse here. In fact, just the opposite. I assumed universality to do this analysis. But if there were a collapse, that collapse would have to have happened long before any interaction with a human, which would result in some conscious awareness, because conscious awareness requires interaction with macroscopic systems like eyes and ears, etc. And if there was a collapse, that collapse would have had to have happened long before interaction with those macroscopic systems. So this has been very brief, but if you want further information, there's a longer YouTube video that talks exactly about this on my channel. Also on my blog, Brain in a Vat, inavat.com. And then also there are 2 papers that are available that fully flesh out these concepts. Okay, thank you for your time.